Hi everyone, this is Mrs. Musoff here, and today we're going to be talking a little bit more about logarithmic functions, graphing them, and also solving some equations. Alright, so let's get started. Now we talked a little bit about the parent function of a log function, right? That's either log base b of x, it could be a natural log, it could also be a common log, alright, like just log of x, which is a base 10. Alright, every single logarithmic function is the inverse of an exponential function. So when we talked about exponential functions a while back, we just switched the x's and y's, just like we mentioned in class. So the parent function has a vertical asymptote. I'm just going to write it out. Vertical asymptote of x equals 0. Every parent function has it. And it also always has an x-intercept of 1, 0. Now obviously this is pre-transformations. So transformations can change these things. But we at least always know where to start before we transform. Alright, if we actually have transformations, then we're going to use those transformations in order to figure out where our vertical asymptote would be and where our x-intercept would be. Okay, our vertical asymptote is always x equals 0 and then plus whatever left or right shift we have. And the x-intercept is always 1 plus the right-left shift, and then k, the up-down shift, is the y value. Alright, and these logarithmic functions, just so you know the shape of them, they'll always look something like this. 1, 0, so an x-intercept, they'll have that vertical asymptote at x equals 0, and they'll look something like that. Alright, so that's the general shape. As long as we know the shape, we can do the transformations. So let's try a few. It says list the transformations, state the vertical asymptote and one other point, and then sketch the graph. The graph. Alright, so let's start with our transformations. Alright, this right here is one of those extra numbers that wasn't part of our parent function, so that's a transformation we're going to describe. So that's going to be a shift left 2. And then that's it. That's the only transformation we have. Remember, this is not a transformation. That's just your base. Okay, but it's not a transformation. So not a transformation. So I only have shift left 2. Remember, I'm starting with the point, like the parent function point. So I should say parent is 1, 0, the x-intercept. If I want to shift it, I'm just going to kind of create a table, even though there's only one point. And I'm going to shift left 2. Left 2 means taking my x value and subtracting 2, but keeping the y value the same. So the original x value was 1. I'm subtracting 2 from it, so it's going to be negative 1. But the y value is going to stay the same. Alright? And we can do the same kind of thing with our vertical asymptote. Our parent function has a vertical asymptote of x equals 0. I'm shifting it left 2. Left 2 does affect x, so now my new vertical asymptote is going to be 0 minus 2, so x equals negative 2. Alright, so new vertical asymptote, new point. So I'll plot my point, negative 1, 0, and I'll graph my vertical asymptote, x equals negative 2. And then it's just a rough sketch from here. Okay, approaches the asymptote down here at the bottom and goes off into the abyss at the top. Alright, I know it looks like a lot of work, but a lot of this can be done in your head, so feel free to kind of work with that also. Alright, same thing here in letter B. I've got one transformation right here, so that is a shift right 5. And I have another transformation at the end. That's going to be a shift up 1. Again, the 2 is not a transformation, it's just my base. Okay, so I'm going to organize this a little differently. My parent function has the point 1, 0, and the vertical asymptote x equals 0. My new function is being shifted right 5, that's x plus 5, and up 1, that's y plus 1. So my point will become 1 plus 5, that's 6, 0 plus 1 is 1. And my asymptote will become x equals 0. I'm adding 5 to that, so x equals 5. Alright, so here's my point, and there's my asymptote. So 6, 1 is my point, and asymptote at x equals 5. And from there, again, it's just a rough sketch. Alright, flip it over. Let's try just a couple more to make sure we've got it. Alright, this one's got a few more transformations. So, let's figure them out. I see an x minus 4. That's shift right 4. I see a 2 being multiplied on the outside, so that's a vertical expansion by 2. And then last but not least, this plus 1 on the end is a shift up 1. So again, my parent, you don't have to keep writing this, just sometimes it helps you remember. My parent has 1, 0 and x equals 0. So my new one, I'm going to make my table down here, is shifting right 4. Oops, sorry. Oops. There we go. My new one is shifting right 4. That would be taking x and adding 4. And my y, it's a vertical expansion. That's 2 times y. And then up 1 is plus 1. So my point, which was 1, 0, 1 turns into 5. And 0, 2 times 0, still 0. And then plus 1 is 1. So I have my point at 5, 1. Okay, asymptote, same thing. Asymptote's just x, so x is plus 4. So that'll turn into x equals 4. Alright, so there's my asymptote. And I can roughly sketch it from there. Alright, one more, just so we can see kind of what one other type of transformation does to it. In this one, there's nothing inside because there's no parentheses. So there is a negative out front. That is a reflection over the x-axis because it's vertical. Over the x-axis. And then this plus 2 is outside because there's no parentheses. So that's shift up 2. So again, my parent is 1, 0 and x equals 0. So if I want my new one, oops, let's fix that a little bit. X, well, nothing's happening to x because there's nothing inside, so x is staying the same. But y, I am reflecting, that's putting a negative in front of, and then shifting up 2, that's adding 2. So my parent point, the x stays the same, it's just 1. The y, I'm going to do negative 0, well, that's still 0, and then add 2, so 2. Alright, for my asymptote, it's just x. X is staying the same, so it's x equals 0. And again, just a rough sketch. Alright, we did a little bit of this in class when we went over the homework, so hopefully that helped. But we did a bunch of examples there, so that definitely hopefully helped. Alright, let's try a few more examples now. That's graphing. Now we're going to practice solving. Alright, the nice thing about solving logs is as long as you know how to rewrite it, you should be able to solve almost any log equation, especially the ones we're doing today. So rewriting it means this says log base 3 of x equals 2. My base is 3. Remember, whatever a logarithm equals is your exponent. So 3 to the 2, and then it's going to equal x. Well, this one's already solved. 3 to the 2 is 9, so I have x equals 9, and there we have it. The one thing you do have to remember with log equations that we didn't have to do before is you have to check to see that your solution is in the domain. Because there are times where you get an answer, but then because it's not in the domain of the log, it's not really an answer. Now remember, inside of a log has to be greater than 0. So that's how you can kind of check to see if it works. If x is 9 and I plug that in, 9, which is what's inside my log, will be greater than 0, so it checks out. Okay, let's try it again over here in letter B. So again, I'm going to rewrite it. I have 3 to the 7th equals 3x minus 2. Now I know this says to do it without a calculator. 3 to the 7th is kind of a bigger number. I'm not sure we'd want to do that without a calculator. So I'll help you out with that one. That's 2,187. Usually if we want you to do it without calculator, we'll make the numbers a little more reasonable. Okay, and now here I'm just solving. So add 2, 2,189, and then divide by 3. Alright, do you remember how to tell if something's divisible by 3? All you have to do is add up the digits, and if the digits are divisible by 3, then the number's divisible by 3. So 2 plus 1, that's 3, and 8 is 11, and 9 is 20. That doesn't divide by 3, so I know I can't actually divide this, so I'll just leave my final answer as 2,189 divided by 3. And again, you'll double check. Now, this is kind of a messy one to check, but we can just roughly check it. This is going to be a positive number, right? A decimal, but a positive number. So if I multiply that big of a positive number by 3, it's just going to be a bigger positive number. And if I just subtract a measly 2, it's still going to be positive. So this checks out. Okay. Alright, oh, looks like something didn't show up for me. This should say e. So the natural log of e to the x equals 5. Alright, so to simplify this, remember a natural log has a secret base e down there. So this is really just saying e to the 5th equals e to the x. Well, remember, if I have the same base, I know I can cancel them out, and I can get my answer. So x is going to be 5. Now again, make sure you check. If I were to plug 5 in here, e to the 5th, that's still going to be positive, so it checks out. Okay. Alright, cool. We're not going to do this one yet, okay, because that's an exponential equation. We'll save that for a little bit later. We'll just stick to some of these basic logs. If you have any questions, just make sure you write them down. Otherwise, take a look at that homework, see what you can do. Check those answers. Thanks for listening. See you later.